One of the things that oftentimes really throws people for a loop is this whole notion of expected value of a function. And the reason why it's confusing is that we're used to dealing with functions such as y equals ax plus bx squared by, for every x value that we're interested in, we just simply plug the number in and that gives us the y value. That's a great example of deterministic math. But now that we're in probability math, it doesn't work out that way. That if I wanted the mean value of y just to put in the mean value of x and the mean value of x here as well, will not give me the mean value of y. It may give me an approximation, but it won't be the exact right value as a general rule. Right, so here's why. If you want the mean value of y, by definition, that's equal to the expected value of y. Right, no big deal there. And now that we have an equation for y, let's substitute that in and see if that provides anything of value here. So we'll substitute in ax plus bx squared. Right, straightforward enough. Well, here's one of the great things about the linearity of the expected value function and why it's different than, say, a nonlinear function such as the trigonometric function, sine, cosine, or tangent, right? If we had sine of two angles summed together, that's not equal to the sum of the sine of the individual angles. Right? It doesn't work that way. But here it does. It's a linear operator. We can break this apart into the expected value of ax plus the expected value of bx squared. Further, we can pull out the constants. So that's a times the expected value of x plus b times the expected value of x squared. Again, nonlinear operator wouldn't allow you to do it like that. And you might say, well, okay, I kind of get it, but all you've done really so far is do twice the work, whereas before I just had one simple thing. So how am I closer? Well, let's see here. This first term is really just the mean of x. We have a times mu sub x. And the second term will be b times, hey, wait a minute, that looks recognizable too. Isn't that just the variance of x? No, not quite, but it is related, right? Because if we go back to what the definition of the variance of x was, right, that was expected value of the quantity x minus mu squared, right? And we showed previously how we could break that apart algebraically into the expected value of x squared minus the square of the mean of x. Right, so wow, there's the thing that we're looking for, and we can now come back over and put in the mean of x squared plus the variance of x. And if we now collect some terms here in a very special way, we get a mu of x plus b mu x squared plus b times the variance of x. And I claim to you that that's actually pretty darn useful and illustrative in a couple of pretty fascinating sort of way. Right? Because that first part is exactly what your intuition was telling you that you ought to be able to do here. Because that's just nothing more than our function evaluated at x equal to the mean. That was what deterministic math would have told you to do. And that's also what a first order Taylor series expansion would give us as well. Notice if we didn't have any variance in x, right, then bam, we've got the deterministic expression here. It's because we do have variance in x that changes everything. And that is a very important result here. That is a significant aspect of the influence of variability. So, big picture here, when you want to evaluate a function as a random quantity and you're trying to say what's the mean of that function, you got to be very careful to include the variability terms. And the way you figure out what those variability terms are is to work out this kind of an expression. Now, if it's a linear expression to begin with, then it's straightforward. Bam, you don't have this x squared term to have to deal with. You just get all of the stuff over here that's left over. All the b related terms go away. So linear stuff, hey, this is easy, but with anything that's not a linear expression, then you got to go and do a little bit more work. What we haven't shown is the variance. Variance is a nonlinear operator in some sense, depending on what level you want to look at it, and it's going to get even a lot more complicated than what we've got here.